In the previous lecture, we learned that given a beam segment like this, we can express its end moments in terms of the end rotations, like this. We call these slope deflection equations. In this lecture, we're going to come up with slope deflection equations when the beam segment is subjected to a distributed load like this. We are going to follow our adopted sign convention and show the end rotations and moments in the positive, counterclockwise direction, like this. We need to write two slope deflection equations. We want one equation for defining MAB in terms of theta A, theta B, and W, and another equation for expressing MBA in a similar manner. To get these equations, we are going to employ the superposition strategy we adopted in the previous lecture. We start by writing end rotations for a simply supported beam under three separate loading cases. Then we superimpose the three cases to arrive at our target equations. Here are the three loading cases we need to consider. A simply supported beam subjected to a positive moment at A. The same beam subjected to a positive moment at B, and the beam subjected to a uniformly distributed load. For each case, first we compute member end rotations. Then we combine the individual rotations at each end to come up with the total end rotations. As you'll see in a minute, the right-hand side of these equations can be written in terms of MAB, MBA, and W. This means we can solve them for the end moments in terms of the end rotations and the load magnitude. Here are the details. Loading case 1. The load is a counterclockwise moment placed at A, like this. The beam is going to deflect upward, causing a counterclockwise rotation at A, and the clockwise rotation at B. We refer to the moment as MAB and denote the end rotations as theta A1 and theta B1. We can use the virtual work method to calculate these rotations. Here they are. Loading case 2. The load is a counterclockwise moment placed at B. The bending moment is labelled MBA, and the end rotations are labelled theta A2 and theta B2. Similar to case 1, using the virtual work method, we can easily determine these end rotations. Loading case 3. The load is uniformly distributed over the entire length of the beam, like this. Similar to the previous cases, we use the virtual work method to calculate these end rotations. They are: here is a summary of the three loading cases. If we superimpose these diagrams, we get this diagram. This means rotation A here equals to the sum of these three rotations, or similarly, rotation at B can be written as, in the expanded form, these equations become let's treat MAB and MBA as unknowns and solve for them. To do so, first arrange the two equations like this. Then multiply the first equation by 2 and add it to the second equation. This gives us. Now solve for MAB. Substituting this expression for MAB in one of these equations, we get So for a beam segment under a uniformly distributed load, slope deflection equations are. Let's compare these equations with the ones we got for a load-free beam segment. Here are the two sets of equations side by side. The difference between the two sets is these terms. They can be viewed as the effect of the applied load on the slope deflection equations. We refer to them as fixed end moments. For a uniformly distributed load, fixed end moments are positive WL squared over 12 and negative WL squared over 12. Obviously, different loads give us different fixed end moments. For example, if we subject the beam segment to a downward concentrated load of P at mid-span, fixed end moments become Generically, we can write the slope deflection equations as where FEM sub AB stands for fixed end moment at end A and FEM sub BA represents fixed end moment at end B. So for a uniformly distributed load of W, FEM AB is positive WL squared over 12 and FEM BA is negative WL squared over 12. Note that here too, we are using counterclockwise direction as positive. So this represents a counterclockwise moment, whereas this represents a clockwise moment. Let's use an example to see these equations in action. Here is a continuous beam subjected to a uniformly distributed load. To analyze the beam using the slope deflection method, we are going to separate the joints from the members, like this. For each beam segment, we show the member end moments in the positive direction, like this. Then we write the slope deflection equations for each segment. For segment AB, we get. For segment BC, we have Now show the member end moments acting at each joint. Then write the joint equilibrium equations. We have 3 of them. Substituting the slope deflection expressions in the above equations, we get. Solving these equations simultaneously for the unknown rotations, we get. Now we substitute these values back in the slope deflection equations to determine the member end moments. Knowing the member end moments, we can easily determine member end shear forces. For segment AB, we have. For segment BC, we have. Now we transfer member end shear forces to the joints. So the support reactions are or in the next lecture, we will discuss the formulation of fixed end moments for various load shapes in more details. Here are a couple of exercise problems involving uniformly distributed loads and joint moments only. Analyze the following indeterminate structures using the slope deflection method.